Yes. Yeah, welcome everybody. Thanks a lot, Jensu, for the initiative, for bringing us all together. I'm very much looking forward to the next few days and to continuing the discussions that we already started. In this presentation, I'd like to first introduce you the activities of IBM Quantum. And last week we had our IBM Quantum Summit, which is our yearly event where we have a lot of big announcements. It's perfect timing, and I have a couple of those here, and I'd like to also mention that here. And in addition to that, I'd also like to introduce our group a little bit, our activities, at least to one half. Tomorrow there will also be a second talk where where Ivano will discuss another part of our activities. So this presentation is also split into two. First, I'd like to go through this recent announcement for the IBM Quantum Summit. And this is already was in the talk title here. So here we really lay out our path towards useful quantum computing. And you will see a couple of things here. And the second part is then really on our activities, how we contribute to that in Zurich, what's the focus of our group in Zurich. Okay, so the mission of IBM Quantum is to bring useful quantum computing to the world. And but this is not only quantum computing, it's not only the hardware, it's really up the stack to make this technology useful, to also think about what we do with that, how get we there, and how do we really bridge that from the application to the software, control electronics, to the hardware. And we published our roadmap for that, first version 2019. And this lays out how we want to scale the hardware, what capabilities we have on top, what the software is supposed to do, what we're planning here, and then how this moves towards applications. And you see here, started with the 27 qubits, 65. Last year, we went to 127. For this year, we promised the 433. And then next year, we plan to scale over 1,000 qubits on a single chip. This will be about the limit that we think can be put on a single chip to bring all the signals in and out and so on. And then this was how far it went like in 2019. But then earlier this year, we extended this. You see here that scaling now goes along different dimensions. So not really on a single chip anymore. We have now multiple chips in certain combinations. The first thing will be to really have a classical combination. So you have multiple quantum chips, but they're classically combined. So they share a controller. And this gives us new opportunities, new ways to use this hardware. As David will present tomorrow. So this classical combination of quantum chips is quite interesting. Then beyond that, we plan to combine quantum chips with short distance, short range quantum couplers. So these are really quantum links. It's 3 chips, but with a quantum coupling. And then long range couplers. So this can be across multiple switches. It will be in one switch. And then combinations of all of those. So like in 2025, we plan to really have more than 4,000 qubits in such a system. All right, so this is like the roadmap here. And there are a couple of things on top, but I will talk about them later on. Now, in this first part, I'd like to focus on this chip. And this is not only about 433 qubits, it's really about improving the performance of the quantum devices. And performance is, we define performance in this case in 3 dimensions. It's the scale, number of qubits, the quality, how good these qubits are, what you can do with that, and the speed, how fast you can run things on this device. And unless you really improve all 3, you will not get to really performant quantum device. Now, let's talk about scale first. I had it already on the slide before. We're very proud to present our new 433 Osprey device. This, if you're wondering, it's like this size, or you can fit it in your hand. This is really a very nice achievement that brings together all the different advances from the last year. So like this multi-layer wiring, here this heavy hex architecture of the qubits, and bringing out all these signals through this multi-layer wiring. This was one of the advancements already for the 127 qubit chip that now really enables us to scale to 400 plus qubits. And this device is up and running. This is the connectivity map. You see all the 433 qubits in this heavy hex layout. 4 qubits are alive. You see here the T1 distribution over the qubits. And you see it's around 70 microseconds at the moment on median. And this is quite a common number for our first generation devices. So this is now currently being calibrated and characterized and so on. And early next year, we plan to make this available to our partners. So this is about scale. Then, of course, the next question is about quality. And here, we also made quite some advances. So here you see 2 chips. The one is the 127 first generation Eagle. And this is the 5th generation of the 27 Falcon chip. And again, here you see the distribution of the T1 times over the qubits. And over the last year, we actually managed to increase this by over a factor of 3. So median T1 times are now really like close to half a millisecond. And the long ones are really close to a millisecond. There's quite some advancements in this front. But we didn't only improve the T1 times, we also improved the gate fidelities quite a bit. All this together allowed us to double the quantum volume, actually twice this year. We started with 128 last year, and now we are at 512. And the quantum volume is a metric for the quality of quantum devices, and essentially measures what size of square circuit you can run. And this was achieved not only by better coherence times, also by a new gate architecture. And so we changed from this fixed frequency to this tunable coupler technology that is mentioned here in this paper. And if you have your questions about that, then feel free to ask Daniel. I don't see him. Here. He can certainly tell you more about this new design for the gates. All right. So much about quality. Now let's talk about speed. So this is really how many circuits can be run in a certain time. And we measure this with a metric that we call flops. It's circuit layer operations per second. And let me very briefly explain that. What we do is we run 100 kind of random parameterized quantum volume circuits. Quantum volume circuits at the quantum volume of the device, because that's like the biggest circuit you can expect to get meaningful results from this device. Then we execute 100 shots for each of these 100 random circuits. And then based on this, we determine the parameters for the next circuit. We repeat this 10 times. The idea is that this is kind of a relevant pattern for many quantum algorithms. You can argue about the different numbers, but then you have to agree on something to get a comparable benchmark. And there were many advances in the last year. Things like parametric compilation, how this quantum engine is really like kind of a quantum operating system further down the stack, improvements of the control electronics. And all of this actually led us to quite a significant improvement in speed. So last year around this time, we were around 1,000 flops, so 1,000 circuit layers per second. And recently, this made a huge jump to over 15,000. And we'll see later that this is really a critical element to get towards useful quantum computing. All right, so we go back to the roadmap. We clearly can tick off this device. And as I said, advances not only on the scale, but also quality of speed. Now, how can we use this device to really create value for our users? What can we do with that? Or how can we get to useful applications? And here, again, we have 3 things we'd like to discuss. That's again, performance, from a different angle. How to integrate that and additional capabilities that these chips enable us to use. So as you know, when we deal with quantum computers, we have to deal with noise. And of course, we want to reduce this noise as much as possible, but it still will be there. So the question is, what do we do with it? There can be gate errors. There can be things like errors during idling, while computers are idling. There can be crosstalk. There can be readout errors. We need to be able to handle all of these errors somehow. There are techniques that we call error suppression that can reduce some of them. And with error suppression, we mean that you change the circuit that you're looking at some point. So you inject some other gates, like here, this is illustrating dynamic coupling, but can also be different ways to implement a certain gate with some echo or something like that. But the main point is error suppression does not increase the complexity of what you're doing. just injecting something that otherwise you don't really see in the runtime, for example. In contrast, there's error mitigation, and error mitigation, you also inject gates. There can be random gates, for example, to do some Pauli dwelling. Can also be a bit more systematic approach to scale some noise. But overall, all these techniques have in common that you have multiple circuits, you have an ensemble of circuits, you apply some post-processing, then this gives you an estimate of an observable, of an expectation value. And there are different types of error mitigation techniques. One that we look into at the moment quite a lot is probabilistic error cancellation, because we think that this is a very promising one. What this allows you to do is actually to get noise-free estimates of the observables from a noisy hardware. And let me quickly walk you through that. Here we have the circuit complexity, and here we have the simulation cost. Classically, this is clearly exponential. And so this will be like very quickly problematic to run on a classical computer. If we would have fault-tolerant quantum error correction, then this would be polynomial. But of course, there's quite an overhead, and we first have to get there. Now, with these error mitigation techniques, they also have an exponential overhead. But we think that we can push the pace of this exponential growth to such a small number that it starts at some point to outperform what classical computers are doing. And at the moment, we're not quite there yet, but we hope that soon we will reach that crossover point where with these quantum error mitigation techniques, we can outperform classical computers when simulating certain circuits. Now, of course, to get to a quantum advantage, you have to find the right circuits, but that's a different question. We'll get to that a bit later. This error mitigation technique is probabilistic error cancellation scales as follows. I'd like to quickly walk you through this formula because we get back to that in a second. So the runtime, the overall runtime scales as the rate with which you can run your circuit. So this is kind of the inverse of the flops times the depth of the circuit, how many layers you actually want to run, times this gamma bar, which is a kind of a collective measure of all the noise in the device, to the power of the number of qubits times the depth. So this power is essentially the number of gates you want to run or the number of gates you want to mitigate. And this tells you also why the speed is so important, because this can become quite a large number, but to some extent you can compensate it with the speed, or you can run more interesting circuits. All right, now this is what we're looking into in terms of improving the performance or doing something useful. But then the question is how to integrate that, how to really make this usable for users. And this is where what we call frictionless integration. And for this, we introduced two quantum computational primitives. We call that implicit runtime primitives. We have the sampler and the estimator. And they're actually performing some basic tasks that about every quantum algorithm is relying on. Sampling, you give it a circuit, and you get the distribution back for measuring it. And since there can be some error mitigation, then you don't get a probability, but a quasi-probability distribution. And for the estimator, you give the circuit an observable, and you get the expectation value back. And this allows us to hide all the error mitigation behind the scenes. So you can just use that, and you get that essentially without having to change anything else in your code. And to start with, we introduced a very simple interface. We just have what we call the resilience level. And default is 0, so no error mitigation. But then you can set this to 1. In the sampler, you get a model-based measurement error mitigation technique. In the estimator, you get a model-free measurement error mitigation technique. They're a bit better suited for the different tasks, but they are doing the same. They're correcting the measurement error, and they do not increase a lot of overhead, so they are almost for free in terms of complexity. If you turn this to 2, then for the estimator only, what you get is a zero noise extrapolation. So instead of running the circuit as is, you also run a version of the circuit where you increase the noise. In this case, it's inserting a noisy gate, so you replace the C0 by 3 C0s, which logically should do the same, but it increases the noise. And then you extrapolate to the zero noise limit. And this already increases some overhead because you, instead of running one circuit, you run 2 or 3 circuits, for example. But it's still like not a significant overhead, but it also it often gives a very good result, but not always. And last, if you turn this to 3, then you will get the probabilistic error cancellation. So this is first characterizing the noise of the layers of the circuit after some Pauli drilling, then inserting new random Pauli gates to actually mitigate that noise. And this comes with this exponential overhead that I mentioned. If you manage to get this gamma bar small enough, then this still allows you to run really meaningful results, meaningful circuits to get meaningful results. And this is now available as a first prototype in this estimator. So you can just set this to 3 and you can test this out of the box. Here's a small code snippet which shows you how to do that. So it's really options with the resilience level 3. You start your session and you call the estimator with your circuits observable counterclass. All right. This is about how to integrate that. Now, what is how can we increase the capabilities of the functionality that we can that we provide with this estimator, with these circuits? And here, particularly, want to talk about dynamic circuits. So far, we were only able to run static circuits. We were already allowing mid-circuit measurements, but not reacting on that within a circuit. And this changes now. What we now can do is you run a circuit, you have a mid-circuit measurement, and based on this measurement, you apply some classical logic within the coherence time, and you apply a certain gate. And this is very nice. This allows to do a couple of things. Like in this example, you can have flippered circuits of a certain depth, and you get them to constant depth flippered circuits with double the number of qubits, but at constant depth. And there are also things like QFT, which can be done more efficiently. There is things like circuit coupling, which again we will hear tomorrow from David. So this is a very powerful concept to optimize circuits. And this is now actually rolled out in 18 of our devices. And you have to write Quasar-3 code, but this is documented. Then you can apply this classical logic within the coherence time of a circuit, within a circuit. Right. Back to the roadmap. So it was already on the roadmap, and we're happy that we can also pick off this part. As I mentioned, if we now look further out, there will be larger devices. There will particularly be this classical parallelization next year, and then the larger modular devices. But also things like threaded primitives, which means we have this primitive sampler estimator, but in a parallelized way, which of course will be very interesting in this setting, but also we just have independent classical quantum devices with classical communication. And error mitigation will be further improved in these primitives, and we will also push what we call quantum serverless. So this is a deployment model where the classical and the quantum compute is happening in the cloud, and you essentially just tell your application where you want to run it, like on 3 QPUs, that many CPUs, then you can offload this. Okay, now the last part, or last topic in this first part, I actually like to pose a challenge to you, or we'd like to pose a challenge to the whole community. We call this the 100 times 100 challenge. So with what I've discussed before, with these error mitigation techniques and the scaling and the improved speed and noise, reduced noise, we think that by early 2024, we can build a device, we can build a tool that allows you to run circuits with 100 qubits and 100 depths. And we think that you can run them such that the overhead of error mitigation is less than a day. So this is how this would look like. You have 100 qubits, these different layers, and then you can simulate them in a day. And we are promising to build this device, but we then also ask the community what actually to do with that. It's what I mentioned earlier. We will be able at some point, hopefully by then, to run circuits that you cannot simulate classically, but we have to find the right circuits to have them do something useful, to have that really achieve a quantum advantage. And I think this is a question that is fundamental for the field and that best is answered by the whole community. Here this is illustrated again. This is the same curve, it's not a similar curve as before. So this is the overhead of the error mitigation technique, but now with respect to the error. And this is for a 100 qubit circuit with the depth 100, 400, or 4000. Here you have certain reference lines. So for example, this is our latest Falcon R10 device, which is a median error rate, which is a bit larger than 10 to the minus 3. If we would be able to reach this 10 to the minus 3, then we could run this circuit with a depth 100, the sampling overhead of this error mitigation technique in 1 day. If we significantly, or like actually only reduce the error rate a bit, we can already significantly reduce this overhead or run longer circuits. So this is this challenge, and I think this is very important, and therefore I also like to go a little bit more into the details and the assumptions behind. This is the formula we solved for. Now I plug in numbers here. So 100 layers, 100 qubits, and again 100 layers. So we think that we can get the beta and the gamma bar such that this will be less than 1 day. And so if we go through this fine print here, the device will have a heavy hex connectivity with at least 100 qubits. We think that we can run 100 hardware efficient layers of non-overlapping 2-qubit gates. And then to achieve this goal, we would require a repetition rate of around 100 million circuits per day, which corresponds to about 100,000 clocks. Remember, we were at like 15,000, so we're not like too far away. And on the previous slide, you saw the error rates are currently here. We need to get them below 10 to the minus 3. It's also there, we're not too far away. So we're pretty confident to achieve this goal, which would then correspond to a gamma bar of less than 1.01.
Stefan, what do you mean by noise-free?
That's a good question. By noise-free, it's an unbiased estimator. Okay. But depending on your target accuracy, you still have to repeat it.
Yeah. It's unbiased, which means that the more you sample,
exactly.
the more you converge to the full.
Yeah. What the technique does, and I don't have the time to really go into detail in the presentation, but what it does is it blows up the variance. So you get an unbiased estimator, but with an increase in variance. So you have to compensate that with additional parts. All right. Good. So this is actually the first part with this announcement on the hardware. And there's a video on YouTube since early this week, which is called the Quantum State of Union 2022, where all of this is discussed in way more detail. It's like an hour long. In this link, you also find the references to blog posts for these individual topics where you can also read the more information. I can really recommend that if you're interested in more details of what I presented. Okay, now part 2. Here I have to thoroughly apologize after this very nice and polished slides that obviously I didn't do myself. We now move to a part where we have to do our slides ourselves. So I'm sorry, there might be some break, but I think it's also very interesting content. So this is now the activities that we have in Zurich on applications research and different application domains and on application software development. And we are focusing on 4 application domains. We're talking about optimization, machine learning, finance, and natural sciences, quantum chemistry, quantum physics, etc. And today I want to focus on optimization and machine learning, and all the natural science topics will actually be covered tomorrow by Ivan. All right, so let's start with optimization. I will just give a rough overview now. So I will not deep dive in any of these topics. I want to show a little bit what the different projects were that we worked on, and also tell you a little bit who the people are who worked on that, because I think we have enough time to also discuss and then use the time in the coffee breaks and dinner and so on to deep dive into some of these topics where you're interested in. Okay, so first is on optimization, and particularly on warm starting quantum optimization. That's a project that we work together with Daniel. And the idea is here to take a classical algorithm. We talk about combinatorial optimization. Take a classical algorithm, the best possible classical algorithm that you can find. Use this to find good solutions to your combinatorial optimization problem, and then warm start the quantum algorithm from there. So you kind of have a trivial guarantee that you will be at least as good as the best classical algorithm that you can find. Illustrated this here a bit. So this is a combinatorial optimization problem with 2 variables, binary variables. So just have 4 options. what you can do is you can relax that to a continuous problem, like you can force to be convex. And then this is something you can solve efficiently, classically. And then what you can do with the solution, which will be non-binary usually, but continuous, you can use this to initialize a quantum circuit, which kind of represents the continuous solution by a superposition state of zeros and ones. And then you can start your algorithm like a QAOA algorithm from there to get a good solution at that one. Now, this is the most naive but easiest to visualize variant of this warm starting. You can also do way more complex things using semi-definite programming relaxations of QBOs or things like that. And then warm start the quantum algorithm from there. And we tested this on up to 30 qubits using classical simulation in this case. And that was outperforming all the other techniques and was giving really nice results. Well, this is a very promising technique for quantum computers to maybe improve solutions that you get obtained by classical algorithms. And it immediately tells you what kind of advantage you're looking for. It's not a runtime advantage because you first have to run your classical method. So it's hopefully improving the quality of the solution. Now, we are warm starting it, but it still requires running a quantum algorithm. And QAOA, that was mostly based on QAOA. So we also looked into how QAOA actually scales. And here we investigated all the different things that are necessary to achieve a quantum advantage. So we are really looking into necessary conditions for QAOA to have a quantum advantage. It's not all like rigorously proven, but like I think most people would agree with the assumptions. And I say necessary, this doesn't mean sufficient, but as long as we cannot achieve those conditions, it's very unlikely that the algorithm gives you a quantum advantage. And here you have to really look into how to overcome the limited connectivity. So all the swaps that you have to introduce, and usually these problems are dense, so you require all-to-all connectivity of your qubits, and that introduces a lot of swaps. And these swaps actually make a lot of the runtime of the algorithm. If you don't consider that, then you are overly optimistic about the runtime. Then, of course, this algorithm is often considered in a near-term setting for a noisy device. So we also were looking into how what can we say about the required fidelity of the gates to run this? Because if the gates become too noisy, then you reach a regime where you can efficiently simulate this state classically and sample from a distribution that's close enough. So then there might also be no possibility for quantum advantage. Then last is the runtime. We analyzed this here, how does the runtime scale with the size of the problem? And here you quickly see that this this is going up to about 500 qubits or 500 binary variables. This very quickly reaches like order of magnitudes of our space a month. And then, of course, this quickly rules out certain applications. Sometimes you read things like high frequency trading, probably not. Now there are other results like concentration of parameters, which then significantly bring this down. If you can skip the parameter optimization, that would significantly improve the applicability of that, which would mean that maybe you only have to solve this for a representative instance of your problem, and then you can reuse these parameters for other instances as well. So this is something to look into here. And all these things also led us to a demonstration where we could solve approximate a max cut problem on 27 qubits, run QAOA to depth 2. And this really required all this optimization of swaps, for example. Not true, it's an efficient problem, but optimization for this fidelity and native gate decomposition. And the last project I want to quickly mention in optimization is a variational algorithm for black box binary optimization. So far we are mainly focusing on QBOs and quadratic binary problems, quadratic unconstrained binary problems. Here we drop this assumption of a quadratic problem and allow black box. And we tested this on feature selection. This was the project together with Stefan and Julien. And so here we use variational imaginary time evolution, which is a very, very powerful algorithmic primitive. which allows us to actually also apply two black box functions. And it doesn't scale very well, so we didn't use the vanilla version, but we used the stochastic approximation of it, which Julia and Giuseppe we developed before. And we tested this on feature selection as a black box problem. So the binary variables is determined whether you select a feature or not. And then if you have a certain selection of features, you can train a machine learning model, you can store a machine learning model, and this gives you objective value. And this is the whole black box. So you select features, you train models, you get a score. So you see that these black boxes can become very complicated, but this stochastic or this quantum natural gradient, how we call it, or quantum natural SPSA, this is so generic that you can apply it to such problems, and you still get the kind of the guarantee, it's not a guarantee, but the theoretical motivation from variational imaginary time evolution to get the good results if your parameters are certain powerful enough. When we tested this on real hardware with 20 qubits and on an MPS simulator up to 59 qubits, and you see here some results. I won't go into the details here, but it worked very nicely. And we could find better solutions than comparable classical approaches in this setting with 59 features or 59 qubits. So it seems an algorithm that can really scale is quite generically applicable, and is, I think, a very interesting candidate to achieve like the quantum advantage in optimization. And the nice thing about black box optimization is that it's kind of the most difficult for classical algorithms because you don't have any structure you can exploit. Okay, now the second part is on machine learning. And here I'd like to present two projects. The first is on the power of quantum neural networks, which was a joint project with, among others, David and Christoph. And what we did here, we looked into quantum neural networks, and we wanted to understand how they differ from classical neural networks. Do they have different characteristics? Can we somehow argue that they are more powerful? And this then we looked into a metric which is called the effective dimension. This essentially measures how effectively a statistical model uses its trainable parameters. And what we found is that in a certain setting where we tried to make things comparable, classical neural network used about simplified 60% of the trainable parameters, while the quantum neural networks used more than 90%. So they made a way more effective use of the trainable parameters, which was very nice. So then we also trained them. We saw that the classical networks and the quantum networks trained faster to lower loss values than classical networks. And this was even demonstrated on real hardware. This was a small experiment on 4 qubits, but it was still a very promising result. Now, one has to be a little bit careful because high effective dimension or very effective use of the parameters might also lead to overfitting. And we like in this study, we did not look at a generalization. So this is the next step, but it clearly shows that there is a difference between these models, and now we have to learn how to combine them best to really get more powerful quantum machine learning models. Now, there's a strong relation between quantum neural networks and quantum support vector machines, and there's sometimes the question why you should use quantum neural networks if a quantum support vector machine can actually give you if you want the same, but here you get to the global optimum more efficiently. And we looked into this. We wanted to understand the complexity of these quantum support vector machines, and particularly the sampling complexity, since we only have noisy access to the quantum kernels used for a support vector machine. And we need to learn how accurately you need to estimate all the elements of this kernel matrix. And so we found, and this is a joint work with Can, who is also here, and is also David, and there's also a poster about it next door. We learned that to get the kernel matrix accurately enough for a certain problem where you have m data points, you need a number of samples that scales like m to the 4.67, which is a really large number. I mean, for larger data sets, this very quickly becomes burden. And we also verified that empirically. Now, this is the standard dual optimization of a support vector machine. We also looked at other algorithms, so-called Pegasus algorithm, which is a stochastic subgradient descent algorithm. And that can achieve a scaling which is independent of the size of the data set due to the stochastic gradient descent part. But you see the dependence on epsilon, the accuracy of the result, and epsilon to the 1 over epsilon to the 6 or to the 10, also quite large. Now, in the third column here, you see the complexity of an approximate QSVMs, and an approximate QSVM is a quantum neural network essentially. And here you see this is purely heuristic, so there's no theoretical guarantee, but the empirical scaling, which we like from intuition, you would expect like 1 over epsilon to the 3 from like just how gradient descent algorithms usually work. The empirical scaling really concerns this intuition, and 1 over epsilon to the 3, independent of the size of the data set, again due to stochastic gradient descent techniques, is of course way more competitive than these exact methods here. So this is another like reason why quantum neural networks might be interesting, and it also illustrates some of the pitfalls that you might have in quantum machine learning if you're not carefully analyzing the complexity. All right, that was a rough overview of the applications research, and now I want to give like 1-2 slides on the application software that we are working on. And we built this Qiskit application modules for natural sciences, for finance, for machine learning optimization. These models allow you to actually run these algorithms more or less out of the box, the algorithms in these domains. And this sits on top of Qiskit Terra, which is a layer built with quantum circuits and has the application agnostic algorithms. This leverages these Qiskit runtime primitives that I mentioned. So you immediately can use these advanced error mitigation techniques that I mentioned and try them on our devices, on simulators. And since this is an open interface, other hardware providers can also implement these interfaces for the primitives. So in this stack is provider agnostic in this sense. Want to give you a very brief summary of 2 of these modules, Qiskit Nature and Qiskit Machine Learning. In Qiskit Nature, what we do is we connect classical quantum chemistry codes like PySCF to this application agnostic layers on circuits and algorithms. And we focus on 3 types of problems: electronic structure, relational structure, and lattice models. And we have 3 kinds of tasks that we look into: ground state solving, lattice state solving, and soon to come also Hamiltonian simulation. And then you can use this to build applications on top or to do research on top. So this is our goal, is to have these foundational building blocks as efficiently implemented as possible, so that research can be built on top of that. And for machine learning, the design is similar. We have these gradients, and we send an estimator on top of that with gradients and totalities as subroutines. They are still in Qiskit Terra. Then we have quantum neural network implementations. We have quantum kernels or support vector machines. And you can even connect this to PyTorch. So you can build your PyTorch machine learning or deep learning module where you have classical layers, quantum layers. That goes down to the automatic differentiation. So you get the gradients. You can run all of this with these primitives and the integrated error mitigation. And with this, I'm at the end of my presentation. So I think there are many exciting things to come. Also many exciting things that just have been released. So have a look. They are all available. You can test them. I'm very happy to discuss these things, and the team is very happy to discuss these things over the next 2 days. And this leaves me only 1 last slide. Of course, also want to thank the team very much. A bit more than half of the team is actually here. And if you have any questions, feel free. I think that's a great opportunity to exchange and get to know each other and discuss possible future projects. Thank you very much.
Stefan, and please, question.
Thank you very much, Stefan. I'm really looking forward to try out all these new features of error suppression and mitigation. I have a quick question. Maybe you'll talk more about it, but about the topology of this classical parallelization that you're planning. Are you set on the one which you had illustrated, or are you thinking about the different type of show there?
So what's planned for the next year is really, it's three,
Okay.
or whatever parent devices that have share a classical controller. So that what that means is that you can run these dynamic circuits not just on a single chip, but you essentially can do a mixed circuit measurement here, and then apply within the coherence time of these circuits, apply a gate in the middle of the circuit on the other chip. And this is what David will discuss also tomorrow for the circuit cutting, like how you can actually then use this to reduce the overhead to classically create entanglement between those.
Sorry, one more thing. So you were talking about the. So when we're talking about in the second part, the scaling of QAOA, you said that these are mainly dense systems. Have you tried also sparse systems? Some of the
yeah. So the result that I showed was with the hardware efficient. The results here, you run the manual where on a smart system, on a hardware efficient system. But in many problems, particularly if you have to go from a constraint problem to a QBO, transferring the constraints to a QBO via a penalty term, that very, very quickly gives you a pretty dense system.
That is interesting.
Yeah. And if you can't get an advantage for such a sparse system, then unlikely that we get an advantage for dense systems. So it's definitely valuable to study them as well.
Thanks.
That's good. I would like to ask about this optimization problem. So, what do you consider as the goal of the QAOA? Because depending on the problem, you can. We know that there is a threshold below. So if you can to get better than that optimization, then it's a hard problem also for QAOA. So what's the goal exactly?
You're referring to the conjecture that a quantum computer cannot achieve more than a quadratic speedup for an NP-hard problem.
Essentially.
And
the fact that the optimization problem have a threshold, so you essentially how much you are above the best solution.
So for MaxCut, we know that, or under the unique games conjecture, that we cannot get better than 78% approximation ratio. With a polynomial time.
That's exactly
right. And approximating more than that is then conjectured to be NP-hard. However, these are all worst case statements. And if we would stop at NP-hard problems, we're solving NP-hard problems classically all day, all the time. Every routing problem on Google Maps is an NP-hard problem, and still we get good enough solutions. So the question is, of course, can we prove that it's a global optimum? Very likely not. But can we improve upon classically achieved solutions? Yes, why not for some problems? This depends very much on the problem instance. And it will not work in general, but maybe for some problems we can get better results and they can have a huge impact. Because optimization problems are everywhere.
But the goal is to get better than exactly optimization, or is to get perhaps even a bit worse but faster.
It depends. That depends very much on the application. But you can have both goals. Like I mentioned this here. If you won't start with a classical algorithm, then you can't get faster. Then you can only hope for better. But if you want, let's say you are in this regime where you don't optimize and just sample, where you need many candidates but fast, that might also be an application of QAOA. But QAOA is very nice because there's a theory behind, but it leads to very expensive circuits. I think there needs to be some combination of things like that, imaginary time evolution or stochastic approximations of that, and some way to have a problem-informed circuit design. These things need to bring them together. And they're kind of the extremes. Here, the circuit is 100% derived from the problem. Here, we essentially didn't make any assumptions on the circuit that came from the problem. And I think if we want to really scale this to a quantum advantage, we need to find a middle way.
Sorry, Stefan, I have to ask a relevant and pedantic question. But so why do you have negative P1 in one of your plots? I was a bit worried by this.
I expect that this is just a fit of a function to some data by a designer.
But not more than expansion increasing.
Let me go back to the slide. No, I don't think we have negative ones.
No, I was not before.
Yeah. I think the curve go beyond that. Ah, this one.
Yeah, here.
Yeah. I'm pretty sure this is just a fit of a function without truncation.
It's just a smoothing.
I think it's at zero, probably. It's something that not been measured.
Yeah. So there's certainly a data point here.
The smoothing of an histogram.
This is
Speaking of these histograms, what is more advantageous? Is it more advantageous to get larger median, but with a much larger width? I mean, is there an argument? If you show the next plot, so you have yeah, that one. You have one. So this is clearly an improvement, but can we argue for the fact that this is better, even given this very broad distribution?
I mean, there are 2 points to keep in mind here, and the one is I think these devices have a quantum volume of probably not 500 volt yet, but let's say 500 volt, which is like an 8x8 circuit. So for an 8x8 circuit on a 27 qubit device, you probably find a set of qubits here. So to increase that, you just need to find a good structure of qubits. So that is very nice. If you want to use the full chip, then of course they can harm you quite good. What's not the question, and I cannot answer that, is what's the impact of these qubits on the gamma factor of the factor for the probabilistic error cancellation. And of course, it can also harm you.
But only if you use them.
Yeah, but if you want to run a 27 qubit circuit on this device, then you have to somehow mitigate that. And they're not 100% sure how much they will impact the gamma bar, because the gamma bar is kind of a geometric average over the chip.
One question that I've had for years was in terms of actually running the circuit in hardware. How much of a difference does it make whether you run like 1,000 circuits with 10 shots, where like 1,000 different circuits versus like 10 circuits or 10,000?
Yeah, it makes a lot of difference.
Yeah,
and we it's a thing that's currently heavily investigated and that we're working on improving. So at the moment, the best or the sweet spot is running one circuit with many shots, because you load the pulse sequence once and then you just have to play that again and again. And loading this, compiling and loading this is a bottleneck then. If you need to go to like one shot, many circuits, like the opposite, which would be the statistical optimum for the probabilistic error cancellation. Where do we have that? So here, ideally, like the statistically best performance you get if you run one shot for each of the circuits. That would be the optimum. And that's, of course, really the worst you can do on today's hardware. With these dynamic circuits, what we want to go is that we kind of bake in this randomness into the description of the circuit, that it's essentially not 10,000 random circuits, but it's one dynamic circuit that you play again and again. So this is where we'd like to push to. And we're already there to some extent. At the moment, I think this is implemented by parameterized gates, but since here you wanted to do random powers, you can do this by parameterization. And with this parameterized compiling and so on, you can already reduce the overhead quite a bit because we push this generation of circuits further advanced.
You have like a rough number of like the overhead of 100 times 100.
Yeah, I think he's hiding. I think Julia has even some numbers on the poster.
Yeah, when I configure the
We can talk about it, right?
Yeah.
No, I mean, but it's like this is enough to make kill any damage. It's like 1,000. Yes.
If we don't improve that, it will be large. So if you do a single shot per circuit, then you at the moment will not be at 15,000 flops, for example. That number will go down. So it is something that needs to be improved, and it has been identified as a bottleneck. Actually, not only for error mitigation, it's also for circuit cutting. It's a problem because it's essentially the same technique behind. So this is something but going towards these dynamic circuits will significantly reduce this overlap.
Yeah, our last question,
Okay.
Yes, about the black box. You showed the example applied to feature selection. Do you think it's something we could also extend to do architecture search for example, we could define it as a general.
Yeah, in like conceptually, it looks very simple. There are no assumptions. It's just a binary black box. But it's of course quite heuristic in this sense. And you need to. But the next step is like, can you somehow inform the circuit design for the problems? Can you somehow leverage some features of the problem or characteristics of the problem to construct the circuit?
So some assumptions of symmetries, for example.
Yeah, yeah. I mean, I think so. But this is really like the next step. This is the open question. It's not that we have an answer to that. And these black boxes can also. One thing we did in the papers, we fitted a QUBO to the black box because we wanted to see whether this is a global observable or local observable. Does this imply barren plateaus, like observable induced barren plateaus or not? And here actually you always could find the QUBO that's very close. I mean, in practice that you can't do this. This is exponential, but for these problems up to 20 qubits we could, which was like a nice indication that we likely will not suffer from observable induced barren plateaus. But in general, that's something one has to try.
Yeah. Okay. So thank you very much again. It's very nice. And